Okay, we are live. Okay, thanks everyone for coming out. This is I'm going to introduce Jason Owens and Phillip Mobley from Resonance Group. They have been so kind to come out and speak to us and give us an awesome demonstration on some physics simulation. My name is Justin. I think most of you know me. I'm mostly doing this for online folks and we're recording. But this is Little Codes. If you don't know, it's Little Codes. We meet up every third Thursday here at the Loft. So thank you to the Loft 419 and Erica Ross for hosting us and being so kind and generous. And thank you for showing up in person. So I don't really have much else to do other than to say that if you go to Toledo.codes, the website, you should be able to see our events there. I think most of you know that. And so we do have another event at the end of this month, the 29th, to talk about myself and Jeremy Schroeder went to California to Google I/O. We're gonna do a little debrief on that and a little state of tech from Ohio X as well. I think that's June 29th, I believe, is the date for that. So we'd love to see some of you there. Without further ado, Jason Owens and Phil Mobley. Thank you.
Hello, everybody. Well, thank you very much for coming out tonight. We're glad to have a chance to speak to you all about some of the cool tech that we're currently developing at Resonance Group. I'm Jason Owens. I'm one of the owners of the company and engineering. I focus in embedded systems, and then I have a partner here, Phillip, and you can tell a little bit about.
Sure. So just to give you some background, Resonance Group, we started back in the year 2010. We started out the UT Engineering. Actually, Jason was a recipient at the then time. Dean Nagy, he had like a competition or what was it?
It was through a grant program initiated through the College of Engineering at the time. So I happened to be the first recipient of this grant program that the dean had first put together, and thus Resonance Group was born from that endeavor. And we've been at it ever since then. So.
Yep. And some of our areas that we specialize in, we do a lot in like embedded systems, power management, even IoT wireless, and even AI on the edge, because AI is now the big new hot topic. So I think this kind of fits into our current topic, which is where we're designing a bridge that can combine two programs together in order to do some physics simulation. And we heavily use AI to kind of create that bridge. So, so first I want to start off with why. Why did we build this? Why did we decide that, hey, we should do something to, why should we make this program? So basically one of our internal projects that we're kind of working on is that we want to build what's called a 300 kilowatt traction inverter for EV applications. So traction inverter is just a fancy word to say a motor controller. And this goes inside of like Tesla cars or even inside of, well, any kind of vehicle that uses
electric powertrain.
Yeah, electric powertrain would be good. So basically what we're doing is that instead of doing a like AC DC kind of motor design, we decided to take a slightly different approach, and we wanted to do something that was more pulse-based DC. So you can think of it as like a switch reluctance motor almost. And so what we needed to do is that we wanted to simulate the driving stage. We wanted to make sure that the components that we were selecting were able to handle, would be able to handle the application that we needed it to. We needed, like I said, we needed to simulate the drive stage, and we wanted to make sure that what we're adding can be able to run the motor without catastrophic failures inside of it. So one thing I want to also mention is that we are not designing a new motor. That's not the purpose of what we're doing. We are designing the motor controller. So to design the motor controller, we had to simulate the motor characteristics so we can understand how the motor works. We already have a motor from some previous work that we had done, and we will validate our controller against the motor itself. So this obviously came into some challenges. So like I had mentioned before, we were drawing from some previous experience. So Jason and I, before, in the early stages of Resonance Group, we actually worked together on a solar car team at the University of Toledo, and kind of in some ways we were founding members of that group. And during that time, we were working on this particular motor, and we developed version 1 of this motor controller, which had its own issues. So some of the issues is that the driving switches that we were using were constantly blowing up while the motor was running. Literally, in electrical engineering, we have the term of it releases the magic smoke, so to speak. So that's when, it'll get a puff of smoke and then you realize the component doesn't work anymore. So we need to simulate some of the parameters of the circuit. So we want to simulate the drive typology. We want to be able to simulate some of the back EMF, and we also want to simulate some of the motor mechanical properties. So all of these kind of variables go into designing the controller itself. And as you can kind of be aware, this requires a coupled multi-physics problem. So the mechanical geometry affects how the circuit is working, and then the circuit itself kind of affects the mechanical geometry itself. So with that in mind, we decided to hunt. We went on the hunt because this is not our first idea. We didn't want to start building up our own software. So we went on the hunt. We wanted to find some software that can use the SPICE circuit analysis, which for electrical engineers, SPICE is basically the gold standard of any kind of simulation that you're working off of. We first explored open source solutions. Unfortunately, there was no open source solution that was like a complete solution. So that was non-existent. Closed source, it was a little better because we had COMSOL, which is a fairly popular multi-physics program, ANSYS, competitor to COMSOL, and this random one called Stenos. So COMSOL, it does have a circuit simulator in it, but it's non-SPICE, and that has its own issues. ANSYS, also similar situation, has a circuit simulator, but non-SPICE. Also, both of those programs are quite expensive. Stenos is able to couple with another program called LT-SPICE, which is a program that Jason and I use to design our power electronic circuits. However, Stenos is only meant for wireless power transmission, not so much motor design. So we came to the conclusion that unfortunately we have to build our own simulation software. Yeah, we want it to integrate into our existing workflows that we are using because there's no point in trying to make a whole new thing. And so what we did is that we took a program called FEMM, FEMM, and that basically provided the basis for our EMAG simulations. And then we used KiCad and NGSPICE that provides the basis for the SPICE simulations. So let's talk about FEMM and XSPICE. XSPICE, NGSPICE, they're used interchangeably. So coming back to, KiCad, like I said, is the schematic capture. So this is the user-facing simulation setup. So you would go into KiCad, and then you would set up your circuit on how you want, and then you would set up your SPICE parameters that you would want to simulate on. And then NGSPICE, this is the actual, this is the program that actually runs the SPICE engine itself. So this is the transient circuit simulation engine, and also has support for custom code models, which is very important later on. And then, like I said, FEM, this is the finite element magnetic solver that's used to solve for the physical geometry and also the material models. One drawback to this program is that it only operates in the static domain, and we're trying to do a transient simulation. So that's another challenge that we had to solve. And then we have the Python bridge. So this is what the talk is primarily going to be about, is the creation of this Python bridge that is used to communicate between the NGSPICE and the FEM simulations. So just to kind of give a little diagram here for the workings. So like I said, the workflow is relatively simple. So you first start off with your KiCad schematic and simulation setup. So you put that all nice, make it look all nice and good. And then you run it through the NGSPICE, XSPICE. And as this is running, this is actually going to be working off of a custom FEM-XSPICE code model that we've developed. So it's like a little so think of it as like another little component that you can drop into your schematic, and it can basically work the magic. And then this code model then communicates with the Python socket, the Python socket bridge that's here. And this is what translates the data into something that FEM is then able to understand. And then it orchestrates the running of the FEM simulation to be able to grab all the parameters that we need, such as the back EMF, torque, and the inductance for the different coils that we have. And then it runs the calculation on it, and it feeds that information back into the simulation, the circuit simulation, for the next time step. And basically does this over and over again many, many times. So the architecture for this is quite interesting. So we have the SPICE layer up here at the top of this section. The SPICE layer, which again composes of KiCad schematic, NGSPICE, XSPICE, and also some current source stamps in order to start sending the data over. It communicates with the Python bridge through JSON. So we do have like a little WebSocket that's in there that's able to communicate between the two, because that's how the communication is supposed to work. So inside the Python bridge script, we have the FEM engine and even the FEM interface itself. So the script will then send through Python bindings. It's able to control FEM itself. So we basically tell it what kind of geometry that we want to set up, and then coming back to the whole static thing, because if you remember, FEM is static. So to do the transient, we had to add in the function for the Python bridge in order to constantly redraw the geometry inside of FEM in order to basically create a transient simulation. And also had to do all the math and computing all of the numbers to send it back and communicate between the two different programs. So that was fun. So as you can be aware, that kind of came up with some various technical challenges.
Very much so. So there's a few, well, more than a few technical challenges. Well, the first thing is just how do you automate FEM to begin with? So let me just paint a picture for you. So this entire software stack is running on a Linux server, and FEM is not a Linux native program. It runs in Windows. So the first thing we had to deal with is how do you transfer data back and forth between FEM, which is running in Wine in this particular case. So we have the operating system barrier, and do it in a reasonable way so you can transfer data without corruption, which seems like kind of simple on the surface, but there was a few challenges with that. So in order to do that, we had to create this automation layer, which Phil kind of talked a little bit about earlier. So that was its own problem. But the bigger issue actually here was the simulation convergence problem. And how many of you here have actually worked with SPICE to any extent whatsoever? Okay, well, if anybody who's worked with SPICE, even if it's just for like class, you know it can be very temperamental even on a good day. So in this case, we're basically trying to make it do things it doesn't normally do. So I'm sure you can imagine what sort of fun challenges we came into. But part of the issue was figuring out the best integration method. The KiCad interface, interestingly enough, is also running directly in this headless server, but we had to figure out a way to set it up that you could basically remote into it or pull the interface remotely into your computer. You can do your schematic in a GUI, but when you run the actual software, everything's running through scripts in the console-based environment. And of course, logging and debugging is really important so that you can understand what's actually happening while all this is taking place.
Simulation challenges.
Yeah, so coming back to the simulation challenges. So SPICE is inherently unstable under a lot of edge cases. And the biggest issue is because we're trying to do a transient simulation with a program that is inherently meant for magnetostatic or electrostatic analysis. So what we're basically doing is we're basically trying to figure out the time step to make the next time step be so that the change in flux or the change in current or the change in this parameter is not so large that causes the SPICE engine to go unstable and basically crash. And that happens a lot. Now, the nice thing is SPICE inherently figures out how to do that, which is good if you can set the right simulation parameters. So that was the dance that we had to walk. And of course, transient history, that's its own problem. I won't go into that too much, but I'll just say this, like when you're doing the simulation, the time step that you choose will also dictate how accurate the result is. So having a variable time step according to the change in values and a bunch of other parameters affected the overall accuracy of the simulation. It does not like tools changes, by the way, which is unfortunately the very situation we're trying to simulate. So that's a particularly interesting challenge. State variables, this is another really important thing. Keeping track of the state of the model. So if you imagine, for example, let's say we're rotating the motor, you need to keep track of, let's say, the position that the rotor was in during each time step. And as you advance the rotor, you have to make sure that you can do it reliably so that you don't introduce incremental error. So basically, the position of the motor has to match the time step, and it has to match the physics. So that code model in the SPICE engine is handling all of the circuit parameters, but the Python bridge is not only handling circuit parameters, it's also handling the physics of the motor. So we're taking into account the mass of the rotor, the acceleration of the rotor, the inertia of the rotor. So that way all those things can be factored in the equation while we're actually simulating the voltages and currents. So those state variables are all maintained within the system as it's running. And of course, feedback loops, we all know those can be quite fun. So just to give you an example of something that didn't work so well, I was in one of my most recent circuits we did with this. We were trying to simulate a simple switching circuit that was just kind of reversing the current going through the motor windings to make it spin, right? And the physics engine worked fantastically well because you saw the motor accelerating slowly, and then at a certain time step, suddenly the velocity increased like by 25 times, and it's like somebody gave it a giant kick to get the thing spinning. And then I went back and took a look at the circuit, and apparently there was a convergence issue. And at one point, it burped out like 5,000 amps into the motor, which of course created a giant step torque, and then it sent it off like a jackrabbit. So the physics work great, but if the circuit simulation is not doing what it's supposed to do, that can create some interesting problems. So, and performance trade-offs, I touched on this a little bit earlier. The biggest thing here is knowing how accurate you want to be versus how long you want to wait for the result. So we had to come up with some ideas of how to best mitigate that, which typically for these types of problems, we'll start with a low resolution simulation. So you can hunt through the problem space and figure out where you want to focus, and then you can kind of dial it in a little bit more within certain areas to help save time with the simulation analysis. So this is one of those things that we're working into this program so that we can figure out where we want to focus most of our time when we're solving problems.
Mm-hmm. All right, so what does this actually enable us to do? Well, what we were able to do with this program set that we have, we were able to simulate the motor startup behavior for our own custom motor, obviously. Later, we were able to set it up for generator loading. So later on in the not so distant future, we're going to be simulating some generators inside of it, some custom spec generators. That will also be able to tell us how much power we can generate, how to drive the generator, or how to pull certain power off of the generator, and under what conditions the generator is able to operate in. Later on, we'll also be working on doing some transformer transient responses, and we can also figure out what the inductor saturation is. So this is very important, even for our own motor that we're working off of, to make sure we don't saturate the inductor core. Because if you saturate that, then your performance in the motor or even the generator or a transformer will significantly decrease. And then what we want to do is that we also want to take this and do some magnetic switching devices, and later on do some experimental electromagnetic machines so we can simulate more of the nonlinearities of the magnetic core material. So now we get to some more interesting stuff. So with all that being said, so here is the circuit that we created inside of KiCad. And these are the voltage and currents plots that we actually got in real time. And then this is a nice little animation of all of the simulation steps that it took in order for FEM to basically, for this circuit, to be able to drive this motor and then to create our voltage and current plots that you see here. So, Jason, maybe you can describe a little bit.
So this is actually a simple simulation of a two-phase motor. So what this is here in the center, this is a diametric permanent magnet that's in the middle. And what we're doing is we're starting from t = 0 when the magnet is not moving at all. This here is the rotational position right here. And what you can see here is that the field is already at a constant velocity as it's rotating. And what happens is, because the field's rotating, in this case, I think I had it set to 60 hertz. The magnet doesn't immediately catch the field, but you can see with each cycle, it kind of starts to accelerate through the field. So And the other thing that you can start to see that you wouldn't see from a typical motor model is you can actually see some of the more intricate field dynamics. Like notice right here, you can see where the flux density is increasing and decreasing as it rotates. What you're seeing there is this is where the magnetic field poles are actually opposing and aiding the rotating field poles. So you can capture some of those more minute details that you otherwise wouldn't see from a bulk model, and also some of the field dynamics and mechanics of it as it actually accelerates. So.
Yeah, so this was comparatively speaking, this was a simple simulation. So then we took the next step and we were like, okay, how about we actually simulate our actual motor that we have? So this is just a couple time steps here for our actual motor. So these are the stators that you see here. These stators, there's coils on each side of the stator, and between each stator, there's a little magnet there. And then of course that goes in a giant circle. And then here, these are where the actual rotor is. So as you can see here, this is also again another voltage plot, and then this is the circuit that's driving it. So.
Yep, and in this case, we're doing a simulation where we apply a current, and then we're looking at the response of the motor to the torque that's applied to it. So it actually is similar to the other one, but in this case, it's a different geometry with much more complex dynamics going on. So here, this would be an example of a problem that would be, I would say, almost prohibitively difficult to model as a magnetic equivalent circuit. You could probably get close, but here in FEM, you can capture all of these minute details, especially the geometry-dependent flux densities and some of these things that would affect the circuit behavior a lot more accurately using FEM as opposed to a bulk model of the same device.
So, yep. So this is just kind of a little bit of a huge intro on the actual program that we've been kind of working on. But I think one of the big things that that really helped us in creating this was the AI tools that we use.
And that is where the real challenge comes in, because part of the challenge is making the actual program itself, which is of course got its issues. But this was also a good learning process for us, knowing how to take AI and use it as a tool to build something that, one, can't hallucinate the code because you need it to be physically accurate, right? So some of the questions that come into mind is like, okay, we built this program, but how do you confirm that it's actually like giving you the right physics, right? These are all things that you have to think about. But really, how do you drive AI agent to build this program in a way that is deterministic with a technology that is inherently non-deterministic? That's what we'll talk about next now.
So I'll pass it over to Jason, and he can talk a little bit more on the agentic workflow.
All right. So before I get into how we built the program with AI, I'll share a little bit about my own journey working with AI. So how many of you jumped into the AI bandwagon back in 2023 when ChatGPT first kind of came out? Okay, so I think you'll all be somewhat familiar with this kind of evolution. I think we all maybe went through something like this from one extent to another. So the most basic form is everybody started with ChatGPT. GPT 3.5 Turbo was like the cat's meow back at the time. It couldn't really code very well, but it made you think it could code really well, so we tried to use it. It was great. And then later on, GitHub came out with GitHub Copilot, and that was pretty awesome. That was when everybody was jumping into VS Code and realizing, oh man, I can actually do code completion. This is pretty cool. So use that for a while. I mean, of course, that's also limited. And then later, we had my first introduction to what I call agentic programming was with the Klein plugin, which was basically an AI agent that lives in VS Code. But unlike just doing code completions, you could actually have it run terminal commands, which give you way more power than just doing code completion. And now, later on, where my path took me was specifically working with a framework called Letta, which if any of you guys went to the AI conference back in October, I talked a lot more about this particular framework, but it basically enables your agents to have effectively infinite memory. And I will say that this framework here was the single thing that enabled me to really do this program in a practical way. Now, I'll share more about that later. Then the bigger vista, which is what I'm entering into now, and use this, is using AI agents as more than just a tool, but to actually manage entire workflows and projects, which was also a critical component to allow this project to come into being. So I want to talk a little bit about how that works. So this is another aspect of the same thing. again, if you're in ChatGPT, you're pretty limited to just question answer format. I think we all know about that. But with the coding assistant, you now have a slightly larger window where you can do a little bit more, right? It can give you code, and you can look at the code, you can copy and paste the code, you can to a certain extent manipulate your program, but it's still very much the humans in the loop. There's still a lot of work on your part. But as we move from left to right, what we start to see is greater and greater levels of autonomy, which is a good thing and a bad thing, depending on how you look at it. And then we get into so-called coding agents, which really the only difference between a coding assistant and a coding agent is you basically get a terminal, which is the single biggest enabler that really spurred on this entire movement of agentic coding. But then we come to the bigger part, which is an engineering agent. And this is where it's not really just about having a good model to work with, but you also need to have the tool harness to operate the model. How many of you guys heard about the whole Claude Code thing when it happened? They open source the code. What was the big lesson everybody learned from looking at Claude Code source code? They had ridiculous amounts of code in there that was just focused on aligning the model and getting the model to do what you wanted. Like literally, like half the program was a giant prompt, it seemed like. But there's a lesson to learn from that, because they figured out that in order to get these agents to really perform, you need to give it really clear instructions, and you need to handle all the little edge cases where the model not perform. Now, I solved that same problem in a very different way. I didn't give my agent tons of prompts all at once and have it do everything. But because I worked with an agent that had memory, I was able to train the agent over time. So if you look back at my agent's memory file system, it probably has hundreds of thousands of lines of memory data, because I worked with it over a course of like 3 or 4 months, fine-tuning it, using it. But we'll talk a little bit more about what actually happened with that. So I think I got a little bit ahead of myself. So what is it that makes an agent an agent? So what's the difference between an agent versus a chatbot versus just an assistant? The main thing is there's a few key ingredients that are really, really important. So the first one is you have to have a good model. And there's no compromising this. I'm not afraid to tell you that I spent more than 50% of the time coding this simulation program using Opus. This is not even a Sonnet level job. Basically, if you're not using Opus, go home for something at this level. Now, it does not mean that you can't use, I want to say dumber models, but you have to know when to use them and when not to use them. But if you need to reason over something that is very complex, very involved, or requires a lot of, say, synthesis of lots of different data, that's where using the appropriate foundation model is really key in this particular case. The other important thing is the instructions and system prompt that you give the model. I think we all know that, but it's even more important with agents, because you're not only telling them how to behave, but you're also giving them your coding preferences. You're giving them all the information about the framework you're using, the documentation. Because if they're going to code this thing accurately, they need to know how to code it properly. They have to know not to rely on their own memory, which is almost always off, because we're always, as developers, using the latest whatever. So you always have to have that documentation available, and you have to ensure that the agent accesses the documentation whenever it needs to do something. But this here, I'd say, is probably the single most important thing, because as the agent does things and makes mistakes, and it learns from those mistakes, if those learnings are only captured inside the context window, then as soon as that context window gets impacted or refreshed, you're going to lose all those learnings. And the next time you use the agent, you have to do it again. And when you're working with a really giant code base and complex systems with lots of moving parts, it becomes literally impossible to move anything forward, because you're constantly babysitting the agent to do the thing that it learned how to do 5 times before. So memory is basically what saves you, because each time you come back to the agent, every time you have a new session, it's really not a new session, because you're building from the previous session. File access, I think that's a fairly obvious thing. This is where we're going to put our documentation. This is where it's going to access the code base. It needs access to resources, right? Tools, that goes without saying. In our case, the biggest tool is the bash console. So if you give it a terminal, you pretty much have everything you need to do whatever you need to do. Shell access, which is obviously the big thing here, I mentioned before. And then permissions and approval policy. So this is another reason why a foundation model is not optional for this kind of an endeavor. We actually do have a local AI model that we run on our infrastructure. It's a Qwen 3.6 35B model. It works great if you're doing really simple stuff with it. You can do code completions, it can do research like a champ. It handles IT stuff fairly well, depending on what you're doing. But I would never put it into a project like this. And the reason is because the dumber the model is, the more that it happens to hallucinate and disobey instructions that you give it, or try to overthink whatever you told it to do. So best case scenario, it gets stuck in the loop overthinking. Worst case scenario, it goes off and does something you never told it to do and creates problems. So one of the things I found with any big project like this, you want to work with foundation models. I was working with Sonnet 4.6 at the time and GPT 5.4 at the time. And basically, if I wasn't working with those models in the critical points, I wasn't going to go anywhere. But you have to be able to use a model that you can trust to say, hey, I can give you full shell access without approving every command, because I had times where these models were running for literally hours at a time, grinding through the code base and going through documentation. And because I gave it all the instructions up front, it knew how to do those things, and it also was able to self-correct itself as it worked through some of the challenges. So then I could basically come back in an hour and be like, okay, where are things at? And then it could give me a status report. Okay, here's what's working, here's what's not working, here's the part that I'm really struggling with, and then I could give it more specific directions. But this is where you graduate from a coding agent to what we call an engineering agent, because it's mostly autonomous. But again, that only works with the good models. Last one is human review. So the way that I structured my workflow with this oftentimes is I would set with the model and we would go through the design, come up with a spec to follow, and then I would have checkpoints where I'd say, okay, here's phase 1, phase 2, phase 3. When you get to the end of phase 3, give me a report and we can discuss it and decide if we need to change the course of action to move forward. And so you have structured, you could call it a code review actually, but you're basically having a code review with your agent to move through some of the details. So I mentioned this earlier, but it goes without saying, the tool harness is obviously the biggest important thing in this case, because the agent is only as good as the tools that you give it. But there's also a point of no return where giving too many tools or not the right tools doesn't benefit you either. So one of the things I'm going to talk about a little bit later, the terminal and how I actually engage with the agent, because there's multiple engagement mechanisms that you can use. But as I said, the biggest important tool of all is the terminal. And when we talk about the terminal, we're not just meaning the agent works in the vacuum and you have no oversight. This is where I learned about this wonderful program called FEMM-XSPICE, which I love to use, and I use it almost every day now. But basically what it allows you to do is you can open a FEMM-XSPICE session either on your own console or on a remote machine, anywhere that you can get an SSH connection. And then the agent can also join the same session, so you can actually monitor live what the agent's doing. So as it's typing commands and running stuff, I can go back and I can monitor the command history. I can also type commands into the same window that the agent's using. So it allows both of you to basically do pair programming or pair console access together. And that's a really great way for oversight and monitoring things, especially if it's a complex operation. So that's a really great way to do that. And in addition to the console, which was my primary means was the console. So for all of you who love GUIs, that's fine. It still works too, but I actually kind of, during this time of my life, this is when I learned to love the console. So if you use Claude Code, I use a program called Metacode, which is basically a clone of Claude Code, but it uses the memory-based agents to do the same thing. And that was my primary interface. Now, let's say I'm not in front of the computer, but I want to still be able to monitor things. I also use Telegram, which is basically the same program everybody's using, OpenClaw, same program, right? So I do this if I'm away from my computer. I want to check in with the agent on my phone. You know, just say, hey, how's it going? It can give me an update report, or it can give me notifications if something's going wrong. I also like to use voice chat for some limited cases. Now, voice chat is a really great interface if you want to brainstorm. So how many of you guys have heard of spec-driven development for agents? Okay. Now, this is really, I'm a big fan of that, but I'm not a big fan of sitting down there and writing all that stuff out, even the prompt to help the agent write its own spec. What I like to do is brainstorm. So when I first started this project with Phil, the first thing that we did was we sat down and said, okay, here's the high-level goal of what we want this thing to be able to do. I had no idea how to even approach this when I first started. Like, we knew we wanted to use FEM, we knew we wanted to use KiCad, but we had no idea how to make these things talk to each other. So part of that brainstorming process was me just getting on a voice chat with my agent and saying, hey, here's the the desktop X procession. Now, this is really great once you are ready to start using the system that you produced. So again, this whole platform is running on a headless server, so there's no monitor to go to look at it. So we set up an XPrep program, which basically is like remote desktop, but the difference is, or it's similar to an X11 session if you've ever used X11. But the difference is if I'm running a program over X11 and I lose my SSH connection, then it basically terminates the program, which is obviously bad if you're running like an hours long simulation. So what XProd does is it actually creates an independent display session on the remote server so you can connect into the display, and then the program will appear on your local machine. But if I close I want to come back to this autonomy and guardrails thing because this is always the big challenge with working with agents. So as I mentioned earlier, one of the key pieces is knowing what model you're using. And especially if you're working with a model that has memory, that's even more important to not change the model midway because different models, once you tune them, they work really well. And if you switch into the wrong model, they can do some bad things. So I learned that the hard way. So this is kind of retracing the same cycle again and again. I'm kind of beating that horse over and over again. So when we're talking about autonomy, right? Basically, it's more of you and less of the AI doing things, right? So ChatGPT is a really good example again, because it can't do anything unless you take the code out and put it in and press play and do it, but you're still the one that's the bottleneck. And then over time, when they started doing like more active things, even in ChatGPT, for example, they had the approval gating, which is better because it can do things without you having to copy and paste code, but you still have to sit there and push a button or say yes or whatever, which is okay if it's something really mission critical. But if you want to be able to get real work done, you have to be able to trust the agent that you're putting together to do the work. That wasn't possible until probably mid last year, I would say, where the agents got stable enough to even allow that. Autonomous read-only exploration. This is something that I started using more extensively with the root code climb type environment because if you're reading files, it's not really going to hurt anything. But the bounded autonomous implementation, that is the part where you have to be very careful. Because let's just put it this way, like, if you're in a coding environment, right, you're in a terminal, your agent effectively has unfettered access to everything on your system because you're in a development environment and you kind of have to do it that way. So how are you going to protect your development environment, your precious code base that you spent months working on to make sure that it doesn't nuke everything? How does that work? So that's a real challenge, right? I'll share a little bit about my experience with that. So long-running agent workflow is where you start to get to when you can get to a high-value, high-trust agent. And I can tell you right now, if for all of us who are fans of how many are fans of open source local model running stuff? Or okay, I'm a big fan of it. I love it, but this is not the workflow for those models. I'm sorry. I'm just going to tell you right now. Basically, you won't make it past level 3 with a local model in this type of workflow because as soon as you get to here, even the model has the best instructions ever, it can still hallucinate and do something it's not supposed to do. And unfortunately, that's just the way it is. I'm sure they're going to continue to get better, but at least my experience so far has shown otherwise. And of course, the last one, step 6, YOLO mode. This is basically completely unfettered access. You're basically saying you have full read-write access to the system, to the code base, to do whatever you need to do. This, you can't even activate with a foundation model until the agent is properly trained. I didn't start using this for probably the first month that I was training my agent, because once you know, let's put it this way, the temperament, that's a good way to put it. All the models have a temperament, like a way that they like to behave, or the way that they think, the way that they react to different things. Like, let's say you're compiling a program and something goes wrong. One model may be more cautious and say, okay, let me take a step back and go back to the documentation. Another model may presume that the issue is X, Y, Z and take action on it, and it could be very wrong. So those kinds of little intricate details you learn just from interacting with the agent more and more and more over time. And I've spent literally hundreds of hours in front of a console doing this stuff, and you start to learn over time what you can safely do and what you safely can't do. But if you don't have that time and you just flip on yellow mode, you're basically asking for trouble before you even do anything. So I did this after about the first month that I was working with this, and I knew the behavior of the agent, and then it could safely run and do those things. But that's not something you do on day one. Now, I'm going to come back to the memory architecture, because this is the single biggest thing that enables the AI agents to be safe. And if you want to ask, what is a path for me to run a local model to be able to approach doing some of these things, having a really good memory architecture is a key, because it's not just about being able to store stuff long term. It's also how you organize the memory, what kinds of content you put into the memory, and how the agent accesses the memory. So back in the time when we were doing the root code discussion, root code also had a file-based memory system, but the problem is it never used it half the time. You had to tell it, hey, go check your memory. Hey, go do this. Hey, go do that. This is where the particular letter framework that I'm using kind of solves that problem, because it basically aligns the model so that it has the propensity to check into the memory automatically without you having to babysit that. And that becomes important when you're having like hour-long coding sprints with the agent, where you're not there to keep track of what it's doing. You have to be able to rely on the fact that you gave it the instructions and that it's checking those instructions as it's running. So the conversation context is, of course, the one that everybody knows of. Project memory, that's basically root code memory. That's where I put my skill file in there. That's where I put my agents.md file, or I put my project MD file in there, and it knows what the project is. But again, that only gets you so far, because procedural memory is, I'd say, the most important. And this is the one that you build over using the agent over days and weeks and months, because it starts to understand how you think, how you work through problems, and how you deal with problems as they come. Handoff memory, this is talking about like, let's say I give the agent some instructions, and then I go off and I expect it to do those instructions. If I don't have a memory system, as soon as my context window gets compacted, those instructions go away, or they get summarized, and it loses context over time. And basically, eventually, it will forget everything I ever told it, and it will start doing something on its own, which is really bad. So handoff memory is, again, another mechanism where it can keep that instruction that you give it in context all the time, and it survives that memory compaction so that it doesn't lose sight of what it's supposed to be doing. Very critical. And then artifact memory, you can think of this as more like archival memory. So let's say I have documentation or SDKs or something that it needs to reference, but it doesn't need to be in context. This needs to be something that's locally available, so it doesn't have to go out and do Google searches every 5 prompts to try to figure something out. It can access this memory locally, it's there, and it can keep moving quickly. Because remember, foundation models cost money, so the more time you spend Google searching, the more tokens you're burning, the more money you're spending. So that's also a factor to keep in mind too. So I mentioned this briefly earlier. Spec-driven development is your friend. And this is what allows you to build a large, complex system that will work as you designed it to work, as opposed to building something that, vibe coding gets a lot of jokes because people vibe code stuff and it looks great, but it works like trash. And the reason it works like trash is because you don't give the agent enough detailed instructions to build it. And when it does, if you do give it instructions, you don't give it a way to follow the instructions accurately. So this is where the spec-driven development cycle really comes in handy. So of course, as I mentioned before, the high-level goals, that's where you have the brainstorming session. That's where you talk through what you want, even you don't even understand how to make it happen, but you have an idea, and then you have the agent go out and take your idea and formulate it into a decisive list of requirements, because that is what you're going to be building your software based on. But in reality, you may not know what those requirements are, so you'll have an initial idea. Like for example, we wanted to use XSPICE. XSPICE, we wanted to use FEM, but we had no idea how we were going to make the two talk to each other. So the next thing is you go out and you have your AI go out and do research. Now, the AI that does the research does not necessarily need to be the same AI that's doing the coding. In my case, I tried all the different ones, and I got research reports, and I coalesced it together. And then I gave those to the coding agent so that it can view all that information, and then we would take that and refine the specification. So at this point, this is where you have a very detailed spec, you have a plan, you have a way to execute the plan, and you have documentation to back it up so that if you run into a problem, you have something to refer to that assists you in the process. So in our case, that resource source was, for example, the XSPICE documentation from SPICE engine. It was the documentation for KiCad and FEM. All the manuals needed to have all the APIs and programming interfaces were downloaded into the agent workspace so that it could have access to that at any moment when it needed it. And then from there, we have the phased execution plan. So for example, in the case of this simulator, you can't just say, go one-shot the whole simulator. I guarantee you'll fail. So what I did was we designed a phase plan where I said, okay, let's work on each piece of this workflow one at a time. So let's just see if we can, A, install the thing on the computer and make sure that we can just simulate something in XSPICE, because the simulator itself doesn't even work, and you can't do much from there. So that was phase 0, for example. Phase 1 might be, okay, let's build our custom code model that allows us to put in some arbitrary circuit parameters and then send them somewhere. It can be like this black box that we'll call FEM. It'd be like basically like a surrogate FEM model, for example. So we confirm, okay, now in order to make this custom code model, I need to download the XSPICE source code and literally compile the entire SPICE engine from scratch so that I can build my code model. So that was an entire phase just to do that. Phase 3 was, okay, now I have the SPICE engine working. I have my code model working. I have a way for me to send information to something. So now I need to build that something over here and test that by itself in isolation. So now, okay, let's install FEM. Let's get wine working. Let's deal with all the Linux ridiculousness of just getting FEM running in wine. That's a phase by itself, right? So at the end of the day, you have these phases where you build each component, test each component. You have a standard interface that you can test against each component. So by the time you put the entire system together, you know it's going to function according to your spec because you've already thoroughly vetted each piece. And that saves you a lot of headaches. And then, of course, you have the system level problems that you have to deal with, but they're typically a lot less at that point. And lastly, coding sprints. So the phases are executed in sprints. So the agent will do a piece, give you the results, give you logs, give you feedback, and you can either redirect it or refine it or tell it, hey, good job, keep going. And I did a little bit of all three, depending on what happened. And so behind all this, you have to know how to talk to the agent, give it the information that it needs, so that it can do its job really, really well. So the first thing is you need to know what you want up front. Even if you don't know how to get it, know what you want. Because if you come in and you're confused, then the agent's going to be confused. And it's going to be trying to figure out and read between the lines of your intent. And if it's not clear, then that will basically dictate the result that you get. You need to give it definite constraints. And again, you don't necessarily have to know what all the constraints are. All these things can be worked out in the brainstorming phase. And the acceptance criteria is equally important because that dictates to the agent when it's done and when it knows it's done a good job and when it knows it's delivering the thing that you asked it for. But that needs to be clearly framed as well. Number 2, ask for a plan before implementation. Yes, that's part of the brainstorming process. If you don't ask for a plan, it's just going to jump into the code and start writing stuff and you'll have no clue what's going on. So part of the prompting strategy is making sure that that plan is generated as it's working, and that as it executes, it checks off a list and says, hey, I did this, I did that, I did that, and you can follow the progress decisively through each step. You also need to make the agent state its assumptions, which is also equally important because I had so many problems, especially with the SPICE engine, where I ran a simulation and it did something really weird. And I'm like, why did it do that? And I went back and I said, hey, what'd you do to the SPICE engine to make it do that? It's like, oh, I just assumed that the kernel was always 0 when it was starting. I'm like, no, it's not always 0. It's running at 500 RPM. How can it be 0? Oh, it made the assumption that it was 0. So you have to tell the model, state your assumptions. What are the simplifying assumptions you made, especially for the equations? In our case, our simulator was designed to simulate unusual physics, which means if you're working with a model that is assuming that you're not using unusual physics, it's probably going to omit a lot of parameters in some of your circuit equations that you would expect to be there. Like, for example, I'm simulating nonlinear reluctance motors. There's certain terms in my magnetics equations that I expect to be there that the model doesn't. So that does require you to have a certain level of understanding about how the physics engine works because you have to do it to put the model in check. But if you don't know, because there were also a lot of things I didn't know about the inner depths of the SPICE engine, I said, hey, tell me, what did you assume about this? And then it would tell me, and then I'm like, that doesn't make any sense. Fix it. So these are all things that you can detect as you're working with it. The other thing is, don't try to bite off more than you can chew. Don't tell it to write the entire program in one shot. Make one piece, one module, one component of the program first. Get that working before you build the next one. It'll be a lot easier for you to reason about what's going on and a lot easier for the agent to reason about. Because whether or not you have a memory agent, it still can only hold so much information in its active context at one point. So the less you force into the memory of the agent, the easier time it'll have to process information and fix problems that come along the way. Making your outputs inspectable, what this basically comes down to is have the agent log things or have it watching the log while it's running things. I can't tell you how many times I wasted hours waiting for something to compile for 30 minutes, only to have it fail, and then I had no idea why it failed, and it didn't log it, so guess what I got to do? Have it do it all over again, and didn't actually log it that time. So there's some very, very simple things that can waste hours of time, but also save you hours if you plan ahead properly for what you expect to see and what you don't. And then capture lessons immediately. I cannot tell you how important this is. Now, again, this only works if you have an agent that has memory. If you do not, this is not useful to you. So what I mean after that is, let's say that I did a sprint, the agent ran into a lot of problems, it fixed the problems. Now, before I tell it to go do something else, I say, okay, why don't we go back through what happened here? So what worked, what didn't work? It's literally like you're sitting down and having a review with the agent saying, okay, what problems did you run into? Okay, good. Summarize those things and their solutions and put them into your memory as key points for next time. So the next time it knows, okay, I did this problem, I ran into this issue, and I had the solution over here. It can look all those things up in its memory and it can solve the problem just like that and forward. Whereas if you don't do that, now it gets to solve the problem over and over again. So sometimes these kinds of active sessions at the end are important. Not only does it help the agent understand, but it also helps you understand what's going on so that if you need to rethink how you're doing something, or let's say there's a problem that's coming up all the time, that's a cause to take a pause and reconsider maybe the architecture I'm using isn't good, or maybe how I'm explaining what I want isn't good. So it's good on both ends to have these review sessions. And then last but not least, you want to treat the agent like a junior engineer with superpowers, okay? I don't care if you're using Opus, I don't care if you're using Sonnet. They're all junior engineers at the end of the day, because you know at the end of the day, you're the one that knows the most about what you want and what you're developing. And you can't expect the agent to read your mind, even though they try. And sometimes you're pretty good at it if they get to know you really well. But at the end of the day, you're the one who's got to be in the driver's seat and you have to know what you want. But if you give the agent adequate instructions, you give it adequate resources, and you're using a model with a low rate of hallucination, then you will likely get very, very good results if you follow these principles. And this is what enabled us to get to where we are today. And I believe that as we continue to refine this workflow, I think these are all becoming standard things nowadays. Because I started on this back in, I think it was the end of February when we first started developing this. So it's only been a few months actually to get from nothing to what we have right now. And I'm sure if we were doing this manually, this would be far more than just a few months, maybe a year, just to get to a piece of software that mostly works and mostly works stably. So we have a lot more to go. There's still a lot of things that we want to add to the program, but the key point is really not the software itself. It's really how you approach designing the software. And that's the difference between a vibe coder and an engineer. This is what people are going to be paying us as developers to learn to do, because the architectural thinking is really what gives you the strategic advantage, because everybody has access to agents, everybody has access to AI, but how you use it, how you deploy it, how you make it work for you, that's really what separates one developer from another developer. So I'm sharing this, and we're sharing this with you today to give you an idea of how we approach the problem. Of course, I don't claim to be an expert at this. I think we're all learning as things continue to change quite quickly. But yeah, that's basically what we're doing. So,
Any questions?
yeah.
Somebody, Jeremy.
What's your Linux distro of choice?
My what? Sorry.
Your Linux distro.
Ubuntu.
Ubuntu 18, or no, Ubuntu 22, I think now.
Oh, yeah, the LTS of Ubuntu.
Yeah.
And thanks for sharing that. TMUX handles like multiple connections into the session. Like I'm a big like GNU screen user, but screen that disconnects you.
I started off with screen, and I had the same problem.
Yeah, so
You know
that's great.
Back scrolling.
Okay.
It's a simple feature. You couldn't do that in screen very well.
Yeah,
I
you
can
had
see
to.
my command line
like,
history. That's great.
I'm gonna have to learn some new some new key combinations. Thanks.
Absolutely. I mean, that was my one biggest gripe with it. Like, I go back and it's like, I have no idea what happened. I just saw something died, and that's all I get. You know.
Control A and escape. Yeah.
Oh, okay. Yeah, so that helped. And the other thing is you can have more than one or more than two. You can have as many sessions as you want. It's great. So, yes.
So I have a question. So I'm curious, why did you build the simulation? Like, what are you guys doing with it that required all of this work?
Well, there's several motivations. So one is the programs that we really like to use were really expensive. That's the primary one. And B, really annoying to use because we actually did get some free trials of Console and Magnet. I literally went to every major program provider that had the kind of software we need to use. And I had literally, I think I burned like 2 months of my life that I can't get back. Just on the phone.
Burned 2 months of our life. A lot of tech support people making us figure out what we wanted to do.
And I'm not saying this is a shot against them because I think the software is really great for what it's doing. I just don't think it's good for me as an electrical engineer because most of the problems that they're trying to solve are not necessarily in the domain that we work in typically, which is very circuit heavy. If you want to do like straight up magnetics or electromagnetics or some other domain, they work really well. But it's just that their support for our type of work is not very.
They're good for doing like assumptions for your modeling what you need to model. But then if you want to be able to do like a couple like physics circuit model in order to see the specific like drive characteristics of the motor, then their capabilities are just not there whatsoever.
Yeah. So I'd say those are the two biggest drivers. And because we are an R&D company, we do a lot of source group work within the field of electrical engineering. And one of the most common things that we deal with is, you know, if you're trying to improve a magnetic drive for a motor or generator, or you're trying to build some custom component for a circuit that you're building, sometimes you have to be able to account for these nonlinearities in the component themselves. And that involves not only materials, it involves some of the physical device constraints that you just can't model directly on a circuit simulator. So that is the other motivation for our case of it, because we're trying to explore some of those areas that are less common to look at. So that requires that brought about some requirements for us to do.
Another question over here.
Out of curiosity, are you looking at keeping this to yourselves or eventually licensing the software for other people to use?
That's a great question because when we kind of viewed this on LinkedIn, we had literally someone asking the same question in the comments. So right now, Jason and I have gone back and forth on whether or not we want to open source the project or not. Obviously, we still need to refine it before we can even start considering it. But actually, this is actually laying down the foundation for another type of program that we want to be able to make, which is where we take FEM. Essentially, we take FEM and we take the XSPICE mission. We literally marry the two together inside of one unified interface.
With the advantage that unlike this one, this XSPICE is really running on CPU. This other one that we're working on is going to be inherently KiCad native. Parallel processing is sorely needed for all this kind of stuff. Because right now, neither FEM or XSPICE component can be used. So you can imagine how things
FEM is coded very long time ago, and
like late 90s.
Late 90s, so they don't even have like support for multi-core CPUs inside of it. So it's kind of fairly bottleneck nowadays.
So I imagine that maybe this version, once it's able, will probably open source it because I think there's still some value for it. And even the one that Phil talked about, we need to talk about having like a base version that would be open source and we can have some other premium features that we add to it. But the idea is, like, you know, we were able to get this far because we were able to have an open source solution. And we're also proponents of that too. So something we do want to support as well as, you know, doing something to earn a living as well. So we would like to do it both if we can. So yeah.
Can you talk more about how the page works? The page.
Can you repeat the question in the microphone, please?
Can you talk a bit more about how the Python bridge works?
Sure. I'll go back. Let's go back. And there we go. Okay.
Right here. Okay, so this is the basic stack for the Python bridge. Now, if you can see, the Python bridge is not just really one program, it's actually a combination of programs that are all working in concert with each other. Now, was there something specific you wanted to know about it? Or just overview, or?
Is it transferring information between separate processes?
Yes, it is, because the SPICE engine is one independent process, and then we're communicating with the Python engine. I can call it a Python engine because it's basically a separate process that communicates through a TCP connection. So you can have these two things running on completely separate machines if you really want to. And then the Python engine is communicating with FEM, which is running inside the line process. That's a third process. And then that one is working through file-based IPC. So we kind of have like two different communication layers, effectively three different processes. And then within each process, we may also have threads running different things that are running within each section. But these are the three major chunks, if you will, of that. And then you can subdivide further within each block.
So the SPICE now sends a request, and does it wait for the response?
Good question. Yes, it will have to. And I'll tell you, I've actually been trying to find ways to make it not wait. But the problem is because SPICE is inherently like time-based, you can't really like parallelize it, unfortunately, because we could obviously spawn like 20,000 copies of FEM if we really want to simulate multiple time steps. But because we're doing transient analysis, you're kind of stuck with linear time. Now, if you're doing like an optimization problem where you're like, maybe exploring a problem space with multiple, times running in parallel, then you can do that, and that's possible. But at least for this kind of problem that we're trying to solve, you're kind of stuck with the linear analysis. Now, one of the issues with SPICE, which is continuing to be a challenge, is you're going through the Meeker iteration process when it first starts up. So I didn't know this until I started building this actually, but when the SPICE engine first starts, it has to converge enough for it to say, hey, I'm accurate enough to actually run. But remember, before you ever leave t equals 0, it has to do multiple iterations, which means FEM has to run multiple times before it even starts moving past t equals 0. And so optimizing that process so that you're not running like multiple iterations at each time step is another challenge too. But there's also compromises you have to make on that too. Like, how accurate do you want your initial current to be, and how do you find the initial conditions without it going off to infinity and blowing up before it even starts moving? So these are all things that we have to face and still continue to face with that. But those get more problem-specific challenges. We have to tune into the problem you're solving. So, but yeah.
Are you starting a new FEM one time each time?
I think for each time step, right? So basically, it rotates the model at each new time step, and then you use the data.
So the basic idea is we start the problem with initial conditions like you would normally define, like whether it's zero current. Now, in reality, you can't define the current as 0, so I have to have some vanishingly small current just to get it to compute something, or else it'll blow up, or it'll have some vanishingly small number. And then it uses that to calculate the initial parameters, like the inductance value of FEM. You can't calculate 0 inductance, or it'll be infinity. So you have to give it like 1 amp just so it can give you the initial inductance. And then it'll send that back to the SPICE simulator, which will then say, okay, this is my henry. So I'm going to look at the current voltage and resistance and calculate what I think the next current's going to be. And it's, I think, right? Who doesn't really know. And then it's going to go hunt around that value a few times and see where it changes the least, and then kind of converge on it. And then it'll say, okay, time equals 0. Now I can go to the next time. And hopefully you didn't have to run them 10 times to get there. But once it does that, then we'll just estimate the next time step. And for each time step, you will have at least one FEM simulation. Okay. But in my experience, usually getting past the initial condition is usually the worst of it. Once you get past that, it just kind of goes. Not too bad. Unless you have a sharp transient, which will blow up your simulation very well too. So, okay. Thanks. Any other questions about SPICE or agentic stuff? Or?
I'll ask a question about your use of LEDA.
Sure.
So, I haven't actually tried. I've used LEDA, the memory side of it, but I haven't tried their agent. Can you talk through like what that experience is like? Like, can you leverage your Claude Code subscription or your
Absolutely.
subscription?
Absolutely. I use my ChatGPT subscription exclusively right now with my LEDA agents. And I also can use my local model with LEDA agents too. And one of the things that I really love about LEDA specifically is they came on the scene, and they're kind of like nobody knows they exist. And I think what you're going to find is that once, probably around next year, when robotics starts really becoming big, you're going to see them start blowing up because the robotics people are actually using them right now, but not most of the software people right now. The big advantage is that they spent a lot of their time perfecting memory management. And you're seeing that Anthropic and ChatGPT are starting to implement some forms of memory. Even the Hermes agent that just came out recently, everybody's talking about that. I've been running Hermes instances, and honestly, I'm really disappointed. I'm just gonna be honest. I don't see what the hype is all about. And it's not because it's not good, but because they say it's a self-improving thing. And I realized my agents have been self-improving for months. It's like that's not even a new thing. That's what this whole framework is all about, right? And that's really what makes this useful, especially if you have less powerful models, because as long as the agent can remember stuff, it's automatically smarter. The problem is it's stupid because it doesn't know how to manage the context that it has. So if you give it enough tooling, that actually helps. So I've been able to build like some actual software with our little 30D model running on the server, and it works better compared to running Hermes, which I would compare the temperament of like my Hermes. I have a Hermes agent and I have multiple Letta agents. My Hermes agent was getting stuck in loops with the local model, just trying to go through a Google search and forgetting how to call APIs. And oops, I forgot I need to install this plugin. I'm like, what are you installing? Like, you don't even need to, So it was kind of like random. I don't know what happened. The Letta agent, it'll do the same thing when you first set it up, but once it figures out how to do it, it doesn't keep doing the same mistake over and over and over again. So the big thing that I see it gives us is stability, and it gives you the way to practically do any context training without fine-tuning and some of these other things. Not saying they don't have a place, but at least for most standard classes, it works really, really well for that case.
And I'm assuming you have some system instructions to like reflect or compound after you're done to say what went well, what didn't go well, that sort of thing.
One of the other really nice things is you can actually define the memory architecture for the agent. So at the very least, it has what they call memory blocks, where you can basically have customized memory that always stays in context and survives compaction, which is the key. So I have at least 3 memory blocks in all my agents. I have the human memory block, which basically tells the agent about you, the persona block, which basically tells it about how it is and how you want it to interact with it. And then I call it a active context block, which is basically just scratch pad memory. So if I have preferences or I have specific things I want it to remember across sessions and not lose, like for example, just today, I was working with an agent and I was having it search on DigiKey for some electronic parts. And I gave it specific criteria about the parts I wanted to look for. But as soon as you use the MCP server and it dumps like 10 kilobytes worth of stuff into your memory, you instantly lose all the instructions that you gave it and it forgets what it was doing. But with the Letta agent, it doesn't do that because that memory block is always there no matter what's in the context window, so it never forgets what I told it to do. So just from that simple thing, my local dumb model now suddenly becomes useful and I can actually get real work done with it. So it doesn't have to be something like super deep, but it just really amps up your capability without a lot of effort.
And I'm assuming you're running each agent in some kind of container or isolated in a sandbox environment?
Letta agents work a little bit different. What happens is the agent's memory lives on a Letta server, which you can host in the cloud. They have a cloud service, which I also use. And you have a local server that we host where you can keep all your stuff local to your system. And what's great about that is you can take your agent and you can use it in different AI applications. Like I can use it in OpenWebUI, I can use it in GitHub Copilot Chat, I can use it in Letta code. You can put it in different interfaces and the memory will follow you across whatever application you're using. So I don't have to keep telling it what I want. And I can like pull up my phone and talk to it in Telegram and do voice chat. And all those things are consistent across platforms. So it gives you a really nice way to work with it. And did I answer your question?
Yeah.
Yeah, I went off on a little tangent there. But yeah, so basically you're asking where it lives, right? So yeah, you can have it live locally on your computer. And if you work in a coding environment like Letta Code, then yes, you can basically give it a terminal. Or if the coding environment happens to be in a VM, which I also have a VM too, if I want to give it like a complete environment that it can work in, I have one of those. So I can teleport it there, or I can teleport it to my computer, server, depending on what I need to do with it. So, and the context follows in all these different environments, which is nice.
Very cool. Oh, another question.
You talked about voice chatting to your agents. Could you explain how you do that? Like,
yes,
what tools you use?
I've got at least 3 that I've been working on. One of them I've actually developed custom. I can show you afterwards if you want to see it. The first one is Telegram, because Letterbot, which is kind of like Letta's version of Quadbot when it first came out, OpenClaw, excuse me. When that whole thing came out, they also spun up their own version. So I got on the Letterbot bandwagon, and I set up a VM on my office machine that gives me a nice isolated environment, and then I connect to it through Telegram on my phone. But Telegram doesn't inherently have voice chat enabled by default, at least if you don't want to pay for it. So we have a local TTS and STT engine running in Docker containers. So I had my agent customize the Letterbot container so that I could put my STT and TTS into the local thing. So when I talk on my phone, it's actually sending my voice transcription to our server and then converting it to text, and then when it reads it back out, it's going to the local TTS, and I can hear my agent talking to me. So I basically created a local voice pipeline. So that's on Telegram. We also use OpenWebUI, which is also a really great platform. They also have their own real-time voice thing. Yeah, I mean, once you tune it up, I'll say that. It can be a little unwieldy to set up, but once you get it stable, it works really well. So I use that one's real-time voice agent, and then I have my own customized UI that I started working on months and months ago. It's called Box UI. But I wanted to have something that's like really clean, it's streamlined, and it's basically voice first. And I can hook it in literally any interface, whether it's OpenAI compatible endpoint or whatever. And I can access it from my phone, and it runs on my computer. So that's the other one that I use for doing voice chat with my agents. So there's a lot of ways you can do it. But these all work for different reasons. There's not one interface that's best for everything. It really just depends. So like if I'm doing coding, I'm not going to code with voice UI. I want to see what the agent's doing. I'm going to go in a terminal, or I'm going to go in VS Code, through code, or whatever, so I can see what's going on. So they're all different environments, but they all have their advantages, disadvantages. So yeah.
Very cool.
All right. Any other questions?
Yep, no question.
No.
Oh, no. Oh, okay. You threw me off too. Yeah, hey, everyone, let's give it a round of applause for Phillip and Jason. Thank you. Thank you guys for being here.
Absolutely.
Thank you.
Yeah, this was a lot of fun, really interesting. A lot to unpack. I'm personally not familiar with SPICE and FEM. I'm not a electrical engineer, but this is I'm gonna have a lot of reading to do. I know.
You're gonna write your own SPICE next, right? That's the next thing, right?
Well,
in Rust, right?
Well, we'll continue more about that part, but we're not necessarily creating a SPICE engine. We're using another open source framework that is inherently GPU native, that basically gives you the ability to do what we would like to do in SPICE. So, yeah,
Very cool.
Stay tuned, coming soon.
Yeah. Yes. Thank you for having us. It was a real pleasure to talk with you all and share just a little bit about what we're doing here. So please, if you ever see us on LinkedIn or whatever, please, follow or whatever. We would really appreciate that.
Yeah, but we'll continue posting as things develop. We'd like to put out little blurbs every once in a while to show progress on this. So
Awesome.
yeah,
Well, thanks everyone.
absolutely.
Thank you.